Our next speaker will be Dr. Xi Peng. She received her PhD from Hong Kong University of Science and Technology. She now works for Huawei Hong Kong Technology Lab, and her interests are in network modeling, simulation, performance evaluation, and optimizations. And she'll be talking about some work she's done recently on trying to use deep learning to improve performance modeling. And with that, I'll hand it over to Dr. Xi Peng.
I'm Xi Peng, a researcher from Hong Kong Theory Lab. Today I will present our recent work, DeepQueueNet. This work is aiming at simulating at scale. Okay, so well, network simulator is is an essential tool for operators to estimate network behaviors, especially when they upgrade or scale the networks. However, most pervading network simulations, they are based on discrete event simulation. They can achieve packet-level visibility, but they cannot scale with the size of modern networks. Recently, deep learning-based techniques are introduced to network performance estimation. And here we give a brief overview of the network simulation techniques. We categorize them into 3 classes. The first one is a discrete event simulation. It's a very fundamental and direct method. This method has pros and cons that are known to everybody. And as a more mathematical method, the packet level and the flow level continuous estimators have been developed, including the Q-theoretic estimators, the network calculus, as well as control theoretic estimators. But they are either suffer from high complexity or the coarse granularity. And nowadays, the deep learning-based end-to-end performance estimators have been developed. They regard the whole system as a black box. And they have the advantage in scalability, but now the sort of works are still struggle with visibility as well as generality under diverse scenarios. Okay, so let's look at very important sort of works. RouteNet is a network scale model, and this model they give estimates, path, and link level metrics. Another one is MimicNet. MimicNet can reduces the scope of the deep neural network from the network scale to the cluster scale. It combines the discrete event simulation together with deep learning in its model, and it targets fat tree topologies. So we are confronted with 2 challenges. The first one is, can we further narrow down the scope of the deep neural network-based end-to-end performance estimators? And the second, can we simultaneously achieve packet-level visibility, better generality, and higher scalability? And we try to answer these questions with DeepQueueNet, and we narrow down the scope further to the device scale. So here, let me walk through DeepQueueNet in more detail. There are mainly 3 procedures. The first one, we model devices by applying deep learning at the device level to predict its input and output relationship. By this way, we can achieve the packet level visibility as well as generality to device and traffic generation models. And then with trained devices, we can compose a network by mapping a target topology directly to a neural network architecture. And finally, we run parallel inference by decomposing the network. And this can achieve in scalability to network sizes. So for DeepQueueNet, let's just see the previous mentioned 3 parts one by one. So for modeling devices, actually a device could be a switch, a link, etc., which will add latency to each packet that input in the system. Given the ingress and the egress packet trees of a device, DeepQueueNet can train a device model. This, generally speaking, for a multi-port device, its DeepQueueNet model can be like this. Actually, it composed of two sub-models. Packet level forwarding model, PFM for short, and packet level traffic management model, PTM for short. The former one is actually a tensor multiplication, and the later one is based on the DNN model. And let me. Yeah, and actually we can regard the device as a complicated function, which gives a relationship between the input flow and the output flow. Okay. And here we can see that the PMF and the PTF actually they process packets in batches to enable high scalability, while conventional discrete event simulation they usually process the packet sequentially. So let's show more details about what is PMF and PTF. So for the first one, here we can put the information of a packet into a packet vector, and this is a packet stream of n packets, and the collection of all ingress and egress packet streams can be expressed with T in and T out. And here is our complicated function. Usually, it's very hard to model it, although methods like queuing theory have tried, but they rely on very strong assumptions. First, we look at the first part. It is a PMF, and I will talk this one a minute later. And for this F is actually, we call it a forwarding tensor. And actually, all these three, they are third order tensors. And for F, it's a binary tensor. And when Fijk equals to 1, it means packet K from the egress port I is forwarded to egress port J. And otherwise, this will be 0. And this is element-wise expression about their relationship. And here is an example to show the order of the tensors when you treat a more concrete example. And as for the later one, the delay function, this could be very complicated. So we apply the deep learning method to get an approximation for it. And we use the transformer architecture to do it because we regard it as a sequence-to-sequence model. Here, how to obtain the raw training data set is very critical. The raw training data set mainly we need to get the time steps of the ingress and egress time steps of each packet. And here, if you have real devices, then you can certainly use it. But due to some practical limitations, usually we can only get such raw training data with discrete event simulation. For example, you can use OMNet just as what has been used in the previous sort of works. Or you can use NS-DOPI. NS-DOPI is a discrete event simulation that is pure Poissonic and is also developed by our lab, and now it's available online. And later I will show you the website. It's a convenient tool to do the discrete event simulation to build your own topology, your own device. Yeah, and then we augment the packet vector with features related to the traffic management mechanism and as an input to this transformer. And the output of the transformer will be the delay of each packet. So let's see the training result of a device. So here, this is a parameter of our test bed as well as hyperparameters. And here we use W1, the normalized Wasserstein distance as a performance metric, and the lower is better. Here we can see, first from this figure, we can see that the training is stable and the loss drops quickly. And then we can see that actually we have to admit that the accuracy drops with the increase of the device complexity. But the inference accuracy can be improved by fine-tuning device models. And then with a trained device model, we moved to how to model networks. So here we propose iterative resequencing algorithm, IRSA for short. IRSA can imitate cross-batch errors between the packets. So we provide a theorem in the paper to talk about the convergence of IRSA. And given a network topology G and its diameter D, IRSA is guaranteed to converge within D iterations. And this is some algorithms we prepared in the paper. And actually, this theorem provides an upper bound about how many iterations are needed given a network topology. This can be very useful when you estimate your running time. And here I want to show a toy example about IRSA, because I think it's a little bit abstract. So here we show a toy example on the Fourier fat tree structure. So here we assume that all the hosts have the same sending rate of 3 lambda, and all the packets at each ingress port are uniformly forwarded to the connected egress port uniformly. And the first round, we can see that we see the packet reordering for uplink. Okay, so, okay. Yes, and we ran the inference from the bottom to the core switches. And first, okay, here is the input of 3 lambda rate, and then because they are uniformly divided, so we can see these green links, they are of 2 lambda. But for these links, the red ones, we are still unknown because we don't know the input from the port 2 and 3 of the edge switch. So we put it in a table, and with the green, we mean that they are determined. With red, we show that they need more turns to be determined. And then we go to we keep upstreaming, and we can see that all these green links, these flows, the sequence are fixed, but the red ones, they are undetermined. And we put it in the aggregation table. And later we came to the core table, and since every input, every flow from the port of the core switch is known, then this table is already fixed. And with this table, we can come to the second round. Here I want to mention that although we only focus on the first pod of this structure, actually other pods are very similar. So, and they can be run in parallel. And after the first round iteration, we can see that all the green ones are fixed, and we need to fix the red curves in the second round. Okay, so here is second round for packet reordering for the downlink. And here we, from the aggregation to the edge switches, and we can see that here we can first put these flows there, and we can get the egress port fixed, and so on and so forth. We can get this table determined. So at last, all the flows, they are converged, and all the sequence are fixed. And again, we can run parallel inference for the same layer. And after this round, everything are fixed. We are happy. And then we can show some results about end-to-end performance evaluation. Here we compare different dimensions and with different benchmarks. This is a parameter of the test bed. And here first we try the traffic generality. Here we try 3 different types of traffic patterns. Here the Markovian arrival process, here is a high order one. We use a 5 order of this model. And we only train with, we train our model with raw data from the network as well as some synthetic data generated by this MAP model. And then we do some tests on both on both Poisson and on-off process. And here we can see that all the distributions of delays are quite close to the ground truth by our method. And here is some comparison. The closer to the reference line means the performance is better. And by these figures, we can show that our method can achieve generality for traffic generation models and can provide end-to-end delay distribution. And compared to the benchmarks, our algorithm actually is more stable and always keep the results near to the reference line, while the benchmark can diverge from the reference line when it deals with the traffic it never seen before. Another is the topology generality. We compare 5 types of network topologies here. And because MimicNet mainly focus on fat tree, so we only compare fat tree with it, for it. And for the other topologies, we compare with RotNet. And here we can see that DeepQueueNet provides much closer estimated delay distribution and can construct arbitrary topology with node degree less than k, no greater than k, using a trained key-port switch device model. Okay. And as for the traffic management generality, we consider 2 types of packet schedulers, the strict priority as well as weighted fair queuing. And here we can see that this is for the strict priority, and there are different configurations of WFQ. And from the figure, we can see that our model actually is TM aware, while the current SOTA are mainly insensitive to such TM mechanisms. And we can achieve high accuracy for different configurations of packet schedulers. And the last is the scalability of DeepQueueNet. Here we consider such a fat tree topology so that we can compare with MimicNet. And this is inference time in parallel inference. And we can see that actually we can achieve high scalability with respect to the size of the simulation by parallel inference. And the inference actually can have a linear speed up with a number of GPUs. And we have to admit that currently we perform the division by hand and leave the automatic partitioning techniques as future work. And this is a takeaway of this work. First, we achieve packet-level visibility with expressive device models, and also we provide some generality in different dimensions. And by parallel inference, we can achieve scalability. And by IRSA, we can mitigate the cross-batch errors. Okay, so at the last, we want to mention that you can feel free to use our online sources. Yeah, thank you very much.
We have time for one question. So I'll ask a question.
Okay.
So one of the things you're modeling right now is kind of the switch or device level characteristics. If I have a programmable data plane, it's something where I can easily change it and make it infinitely more complex. How does that change your deep learning approach to actually trying to learn or infer what the switch is doing?
You mean you have a new type of switch?
Yeah.
And how to use it how to get the estimation of it when you put it in a big network?
So when I put it in a big network, but also the fact that I write code that's buggy. So if I'm writing my own switch code, it's going to have bugs, but it's also going to be unpredictable. So how do you try and how would you try and model that?
Okay, that's a very important question. Usually, because if you have a real device, then you can trust it. Maybe you can collect enough ingress and egress packet traces passing through it. Yeah. But if you don't have such a device, but you have an idea of composing a new switch, so the discrete event simulation could be very critical. If it is wrong, then everything goes wrong. Yeah, and so for this kind of, you should be very careful. Yeah. And maybe you can try the NS.Pi. Yeah. I think in that work, we can prevent you from many bugs. Yeah.
Okay, I guess one more question.
Hi. Just a quick one, Holger Karl, Hasso-Plattner Institute. You looked initially on slide 2 or so at discrete event simulators and equated that with packet level simulators. You can do flow level simulation just as well. Did you consider that? Did you compare that? Flow level simulation on scales nicely?
Okay, thank you for the question. So as for the flow level estimator, actually it's also very important, but nowadays to guarantee the user experience, we notice that it is not sufficient to just have the flow level matrix. Sometimes the operators, they care about the packet level matrix. So that's why we have to move to some new techniques. Yeah. Okay.
All right, let's thank our speaker once again. We're running out of time.